Hello, can you hear me?
Yes, we can.
Okay, so let me remind you what happened last time. So we proved a general theorem that a short exact sequence chain complexes induces a long exact sequence homology groups. And we in particular applied it to the case when this triple of short exact this triple of complexes is a singular is a triple of complex appearing in this setup when we have a topological space X and subspace A inside, so we can consider the complex of singular chains in A, complex of singular chains in X, and also a complex of relative singular chains, and they form this triple of complexes which fit into a short exact sequence. And then we obtain, by using this general theorem, we obtain the fact that the following long sequence of homology groups this is a map induced just by inclusion, map induced by the quotient, quotienting singular chain in X, modulo singular chains in A, and then we constructed this rather non-trivial connecting homomorphism which shifts index of the homology group by 1 and returns us back to homology group of A. And then it continues. And we saw a simple example when A is just some one point subspace. So we saw that this the fact that this is a long exact sequence. So it's so at any place here is the kernel of an X map is equal to the image of the previous one. So it's quite restrictive. So knowing, for example, homology group of A and homology group of X, we can determine homology groups, the relative homology groups. And our next goal is will be to we want to develop some technique of finding just the usual homology groups, not relative. And we will show that, in particular, so our goal essentially will be for the rest of the course is to show that under some assumptions, this after some subtleties, which we will clarify, and under some condition on what kind of this subspace, this relative homology group is essentially isomorphic to a homology group of a quotient where we kind of identify all points of the subspace A, and then combined with this short exact sequence, combined with this long exact sequence properties, this will give some tools of calculating homology groups of such quotients. Okay. Goal will be essentially to clarify when this is such relation holds. Okay. And before doing this, we kind of need to develop a bit more techniques dealing with these kind of pairs of topological spaces and subspaces inside them. So consider a situation when we have in some subspace A in topological space X, but we also have a topological space Y and a subspace B there. And then we can consider what is called a map between pairs, where pair is a topological space and a subspace inside. We want to define what we mean by a map from a pair x, a to a pair x, y, b. A map between what we call pairs. Pairs of topological spaces, where one of the second topological space is subspace inside the first one. So it's a map. So what does this mean that we say that we have a map between pairs? This means that we have just a usual continuous map from x to y. So this is a continuous function. But we want to require an additional condition such that f, the image of subspace A here, is contained in B. So this is kind of a natural requirement. So in particular, so if we have, for example, a third pair ZC, and we consider a map to this third pair satisfying the same properties, the composition will be also a map between pairs, because if this inclusion property will be respected under the composition. And moreover, it's a nice thing to consider with respect to our singular chains and homologies. In particular, it induces such map between pairs and induces homomorphism, which we again denote F sharp. So we already know that any map between topological spaces induces a homomorphism between the corresponding chain complexes. So this is as what we had before. But now we can consider this subgroup of chains in A, and here we can consider subgroup of chains in B. And from the fact that f of A was contained in B, it follows that F sharp in A, the image of this subgroup, is contained inside the subgroup Cn of B here. So this is because, again, so F sharp, on each singular simplex here, F sharp acts just by its composition. So if the image, if you have some singular simplex with image in A, and we compose this with map F, which satisfies this property, its image will be necessarily in B. So that's why we have the corresponding inclusion of this of the abelian groups of singular chains, which are generated by singular simplices. And it's also so we know that so in our previous consideration, we showed that this F sharp commutes with our boundary homomorphism. So that means F sharp defines a chain map. And therefore, So from this property that F sharp, the image of Cn of A under F sharp is inside Cn of B, it follows that this map F sharp can be used to construct a map, induced map on the quotient, which we'll also denote by the same symbol F sharp. Consider the map induced on the corresponding quotients. So this will be well defined because, again, an element in the numerator here is mapped to an element in the numerator here. So if you choose a different representative with respect to this quotient, the result will be in the same class. And this is what we denote by definition. The group of relative chains for the pair A and X, and here this group of relative chains pair Y and B. This is just our definitions. Okay. And for this F sharp, now consider it as a map between between these quotients. It's easy to see that this property that it commutes with D still holds. This is because, again, so this is already, so this F sharp just defined in terms of the F sharp on these original groups of singular chains, and it commuted with D, and also D, we know that D respects this inclusion. This property still holds, and this means that this F sharp considered as a homomorphism on these quotient groups is a chain map. Chain map from this chain complex to this chain complex. And therefore, okay, I guess I can write it here. And therefore, so whenever we have a chain map between any pair of abstract chain complexes, we know that it induces well-defined push forward on the corresponding homology groups. This means that this defines a homomorphism, which we again denote by F star, but now F star the map from the relative homology group for the pair X and A to the relative homology group pair Y. Okay. And now we kind of want to consider a property, kind of invariance, the property of invariance under homotopy, the analog of the property of invariance under homotopy, but in the case of relative homology. But first one has to define what do we mean by homotopy between such maps between pairs of topological spaces. So consider F and G be maps So both f and g are maps from pair x and a to pair y and b. Again, this just means that we have chosen some subspace A in X, and here we have chosen subspace Y here, so that for both F and G, the image of A is contained inside B. And then we want to define that equivalence relation on such maps between pairs. So we say that F is homotopic to G. So F and G are homotopic to each other as maps between pairs. If and only if, by definition, there exists F so in the case of the usual homotopy, we consider F to be a map from X times an interval to Y. So far this is as in the case of just usual maps from X to Y. And as before, we want to require that F restricted to the initial point of the interval coincides with our small f here, and the capital F restricted to the end point, to the terminal point of the interval, coincides with map G. So far this is as in the usual homotopy. But now we want to say some restrictions of the, which involve these choices of our subspaces A and B. So we want to require that for any point in interval, F, capital F restricted to the corresponding T satisfies the property which we had before, so that the image of A is inside B. So by construction, we have this property for t equals 0 and t equals 1, because this is should be satisfied by F and G, since they are defined as map between pairs. But we want this to be satisfied for any intermediate T as well. Questions? Okay, now we are ready to state the following proposition about invariance of the relative homology group with respect to homotopy, analogous to the case of non-relative homology groups. Let F and G be a pair of maps between pairs of topological spaces X, comma A, and Y, comma B, so as before. And they are, it's given that they are homotopic as maps between pairs, as we just defined, this equivalence relation, then it follows that the corresponding push forwards on the push forwards which act between the corresponding relative homology groups are the same. And this is F star, what is F star and G star push forwards on these relative homology groups we also just defined. Statement that the forwards are just equal maps. How do we prove this? So essentially we want to refer to the, so we had this statement in non-relative case when f and g was just a pair of maps between topological spaces x and y, and then we showed that if they're homotopic in the usual way, then their push forwards on non-relative homology groups just without this a and b are the same. So this is we already proved, and we will use kind of I will refer to this proof, namely in this proof, as you remember, we defined a certain prism operator. So we consider previously defined prism operator. So we denoted it by capital P, and it was a homomorphism from Cn of x to Cn plus 1 of y. So this prism operator was defined using, if you remember, it was defined using explicit expression of the homotopy. But of course, if you have a homotopy of map between pairs, this is just the usual homotopy with some additional conditions. So we can still use it as the usual homotopy. Defined explicitly using homotopy capital F. And from the definition, it's that we had, it's easy to see that if we consider this prism operator on the subgroup of singular chain inside A, its image will be contained in the subgroup of singular chain in the subspace B. So this is because, so what is, let me remind you how this prism operator, so it was constructed as some sort of using this F. So the construction was essentially involved some sort of subdivision of your prism, which was your simplex times an interval, and then composing, and then using some composition with this capital F. So, but from the fact that F at any point, so we have the condition that F at any point of the interval has a property that its image of subspace A is inside B, it will follow that, so whenever we compose we compose this F with some singular chain which has image in the subspace A, it will automatically have an image contained in the subspace B. So this prism operator will satisfy this property. And therefore, it induces the corresponding prism operator on the, which you can still call prism operator on the quotients. Because of this property of inclusion we have. So if we take a different representative here, which differs by an element here, the result will differ because of our inclusion property. The result will differ by an element in the denominator here. So it's will be well defined, and the property which we had before for the prism operator in the non-relative case, namely we showed satisfies the following identity. The property still holds. On this, when we induce, so consider all these operators or linear homomorphisms, or you can call them operators which are linear homomorphisms. This will be still true because for each of them, for each of these D or G sharp, F sharp, and P, they all satisfy this property that if you for all of these guys which enter here, you have a property that the image of the subgroup Cn of A is contained inside the corresponding Cn of B with proper in proper degree. So essentially, for G sharp and F sharp and this D, we already showed that they give a well-defined homomorphisms on these quotients, and therefore this will automatically hold. And but we know that whenever, like if you have some pair of chain maps between a pair of abstract chain complexes, and there exists what is called this chain homotopy, which satisfies this identity. In this case, this is P. We automatically get the property that the maps, the corresponding induced maps on the homology groups should be the same. So namely, so one can say that this pair of chain maps F sharp and G sharp, now consider it so this is considered as a chain maps between the corresponding relative chain complexes of relative singular chains are chain homotopic. Using our general definition of chain homotopy, which basically means that there exists some homomorphism P which satisfies this identity. And we already know that, okay, from general proposition, we have that this immediately implies that the induced maps on the corresponding homology groups are equal. So this concludes the proof of the proposition. Any questions? So now I want to formulate what is called Excision Theorem. Which probably not going to give you a complete proof, but maybe I'll tell you some idea of the proof, and maybe I'll tell you if I have time. In the next lecture, I will tell you more details. But anyway, consider first the formulation of this theorem. And they have two equivalent versions. So version 1 is the following. Consider Z to be a subspace in A, which is a subspace in X, and such that closure of Z inside interior A. Closure, well, closure you can understand as union of the original subspace with all boundary points. Well, consider it, this is considered closure in X. Okay, and so under this setup, we have a condition, we have the following statement, that inclusion map this is a map, inclusion map, which is a map between pairs. First pair is a complement of Z in X. The ambient space in the pair, and the subspace there is a complement of Z in A. So of course this is because of these inclusions, this is a subspace here. So this is we can consider as a pair, and we can consider a map which is inclusion to the pair X in A. So why is this is a good? Well, this is obviously, I mean, can be considered as a map between pairs because so we have to check that the image of this subspace is inside here, is inside. Well, this is automatic because this I is just inclusion. So for the complement Z, so this is a subspace in X, for which I can consider the inclusion map, and the inclusion restricted to the subspace maps point inside A. It's kind of tautological. And the statement of the theorem that this induces isomorphism. Between the corresponding homology groups. Let me bit shift, it's clear. Write the same thing. Maps, so we consider X minus Z, comma A minus Z included in X, comma A. And here we just have a map I star between the corresponding relative homology group. Statement that this is the isomorphism. So why is it called excision theorem? That's why kind of you can excise from this kind of pair, you can excise a common subspace, and this will do essentially nothing on homology. Excise it simultaneously from A and X. So the homology of this pair with excised Z is the same up to an isomorphism. Okay, the second, the second version of this theorem is the following. So let A and B be a pair of subspaces in X such that they satisfy the following properties: that interior of A united with interior of B gives me the whole X. Which is the interiors of these subspaces should cover X. And then we consider the pair B and a subspace A union, A intersected B inside. So this is obviously a subspace here. And again, we can just consider inclusion map. Well, we consider inclusion from B to our space X. And this will induce inclusion of this intersection to A. Right? Include B in X, and this therefore this intersection is included A. And the statement then is similar, that this induces isomorphism between the corresponding relative homology groups. Okay. Proof, namely, proof will be later, but namely I will give you just, well, depending on how many time I will have left next lecture, I will give you just idea, or, well, I'll give you some idea of the proof today, but if I will have some remaining time in the next lecture, in the next final lecture, I will give you more details. But in any case, the full proof is actually very quite technical, and well, you probably won't be able to follow it anyway on this video. But well, there is this. You can look. Yeah. Anyway, there is a. You can read Hatcher, or you can look up videos of the previous year. Anyway, well, so far, let us just prove in the beginning. Let's just prove that the version 1 is equivalent to version 2. So, okay, how do we relate them? So, okay, you can imagine the following. Basically, yeah. Well, I might not. Yeah. So, okay, in this V1. So, well, let me remind you. So, V1 we had Z inside A inside X, and they satisfy some property. And here we had pair A comma B inside X. And we want to say that these two sets up are just related by saying that B is the same as complement Z in X. Well, first let's see about the statement of theorem. Okay, here we had, well, in both cases, we had a map to XA here and XA here, so here is the same. And here, on the first place, we have B. And here we have X minus Z. So indeed, this is an agreement. And now we want to check that A, under this identification, A intersection with B is the same as A minus Z. Well, let's see. A intersection with B is A intersection of X minus Z. And well, if you want, you can write this kind of Venn diagram. You have ambient space X. Somewhere Z inside. So okay, so this is a setup of the first version, and then there is a subspace A which contains Z, and then we say that B is X minus Z. B is our stuff here, complement. Of Z and X, and then you clearly see that the intersection of A and this complement of sorry, what I want to say is that yeah, this intersection of this of B in A is the same as A is the same as a complement of Z in A. Is indeed what we want, because we wanted to show that this guy here is the same as this guy here. And moreover, okay, now we want to check that these conditions are equivalent to each other. So in the version 1, we had a condition that the closure of Z was inside inside interior of A. I want to see that this is equivalent to the statement that X is a union of interior of A, interior of B. Well, how do we see this? Well, this is can be seen by noting the following. So since B is complement of Z in X, this means that if we remove, this means that Z, the other way around, that Z is complement of B in X. And if you remove, so if you want to, so you can write a kind of X minus B Z, but if you want to add all boundary points to Z, this means you have to remove them from these boundary points from B. So this means that complement the closure of Z is X minus interior of B. Okay, so if you now have this in mind, this becomes more or less obvious. So let's see. So what is this? So let's go this direction. So what does this say? So this says that any point in X is either in interior of A or interior of B. Well, suppose this is not in interior. Suppose this is not in interior of B. If this is not interior of B, then then if it's not interior of B, then it must be in interior of A. But if it's not interior of B, then it's by this relation, then it must be in the complement of Z. So this follows that any point, sorry, in the closure of Z. That follows that any point in the closure of Z is interior of A. Well, the other way around is essentially the same. So if you, so this says that any point, the left-hand side says that any point in the closure of Z must be in interior of A. But if a point, but this tells us that if a point is in the closure of Z, then it does not belong to interior of B. So we get that any point which is not in interior of B must be in interior of A. Well, but then it means that X, any point in X is at least in interior of A or in interior of B. Okay, so this, well, this is just a proof of equivalence relation. So, sorry, of equivalence of two versions. Any questions? Yeah, well, the point is that the first version is kind of more natural to use, but the second version is actually more natural to prove. Well, they're more, yeah, I mean, they in a kind of rather trivial set theoretic way equivalent. Okay, so what is the idea of the proof? So the first one will actually essentially the main technical details will be contained in a certain lemma, and lemma assumes the following setup. So let's U be a collection of subspaces Uj logical space X such that union of their interiors is X. You already see kind of why it can be related to the formulation of excision theorems. If we go just to use this gives you the second version. This is the setup of the second version of the excision theorem. But it's more, yeah, for this kind of a preliminary lemma, it's more natural to consider an arbitrary kind of collection of subspaces. And then consider, so for this collection curly U, which we denote, we can consider a certain subgroup in the group of singular chains in X, which will be denoted by Cn of U, because it depends on this choice of family of subspaces. So how this is defined? This is defined as follows. So it's as a free abelian group. It's generated by singular simplices, namely a map from n simplex to X, which satisfy an additional condition. So in arbitrary maps like this, they generate Cn of X by its definition. But here we want to require an additional condition that we only consider maps such that there exists some J index such that the image of this singular n simplex is contained in one of the subspaces Uj in this collection. Then this kind of X covered by U's. And we only allow kind of simplices which can be contained in one of them, at least one of them, completely. For example, if you let me have something like X. It is this covered by U1, U2, and 3, for example, covered by 3 guys. You can consider something like this. This is contained, for example, completely in U2, but you cannot consider something like this. It's not contained in one of these U's. Okay. Okay, so well, remember that we have this boundary homomorphism which acted on Cn of x and to Cn minus 1 of x. And it's again, so since this Cn u of x is defined just by some condition, some condition of restriction on the condition on the image, where the image belongs. This D respects this condition because D is essentially takes some linear combination of restrictions of the singular simplex on faces. So this boundary homomorphism induces boundary homomorphism on these subgroups Cn u of x. And it satisfies the property that d squared is 0. So this, again, this defines a chain complex. Chain complex, as in general, this is the sequence of abelian groups and homomorphisms between them. So the composition of two consecutive homomorphism is 0. And whenever we have this, whenever we have a chain complex, we can define corresponding homology. Continue here. We can define homology, which we denote by this additional label U, because this, of course, the chain complex depends on the, in principle, it depends. These groups, I mean, by the definition, they depend on the choice of this family of subspaces. We define this Hn u of x as well, just a homology group of the corresponding of this chain complex. General is the kernel of D divided by the image of D at each of these places. Okay. And okay, what we want to say essentially is that this homology group, I want to show that this homology group is isomorphic to our usual singular homology group. And so you can understand this kind of by the far, you can understand like with the statement that if you you want to restrict your all, consider singular chains with simplices generated by simplices small enough so each of them can be fit in one of these subspaces. And the statement that kind of in this restricted in this way, in this the complex of singular chains restricted in this way, we actually don't lose anything when we go to the homology groups. There's kind of no information, we don't lose any information. We can always, it's okay to consider only singular simplices small enough so they can be fit into this into kind of individual subspaces. So what is the formal statement we want to make is the following. Well, part of the statement will be indeed a statement of these isomorphic groups. But more precisely, we'll have the following lemma. So inclusion I so we have, of course, canonical inclusion of these kind of chains, singular chains, where we have restricted them to so that each singular simplex is inside of one of these U's. Obviously, a subgroup in the whole Cn of X. This inclusion is a chain homotopy equivalence. So we have a general statement of what is a chain homotopy. So what does this mean? Let me elaborate. That is they exist. So this is just a definition, essentially, of what is the chain homotopy equivalence. There exists rho homomorphism in the opposite direction. Arbitrary chains to these restricted chains such that this composition of rho with I and the composition opposite order are chain homotopic to identities. Well, if they chain homotopic to identities, we already know that this means that they're induced the corresponding push forwards on the corresponding homology groups. They will be just the same. So in particular, this will imply that rho star times composed with I star is identity, and the other way around, I star composed with R star is just equal to identity. But this will imply that this rho star is left and right inverse to I star. Means that this I star, this kind of immediately follows that rho star. Well, okay, I will write this a bit. This is what I said. I will write it a bit later. But the point is that from this it will follow that I star is which is a homomorphism between the corresponding homology groups, an isomorphism. Here, so the proof quite technical, and I will tell you, due to the fact that I only have one more lecture left. After this one, I will tell you just an idea of the proof. So idea is the following, that so we want to somehow to construct this. Okay, here how to relate this map is just inclusion, but how to construct some sort of natural map from Cn of x to this restrictive x. Well, the idea is that if you have any, for example, just we'll write more or less the same picture which I had before. Suppose we have some cover like this, and we had some singular simplex which we didn't satisfy these properties. Its image wasn't contained in one of these covering spaces. But the point is we can always divide it, and this can be used recursively. You can divide it recursively, and this can be done using what is called barycentric subdivision into pieces, into sub simplices small enough that they will individually if they're small enough, they will satisfy this property. So they will be contained in one of these subspaces U. Divide. So one can divide, subdivide arbitrary singular simplex x which subsimplex small enough and its image contained one of J's. And okay, here I'm not pretending being precise. This is just some kind of intuition. Again, it's just idea of the proof, and one can use this to construct map D such that capital D, which will be from Cn of x to Cn U x. So it will act as some sort of using this division procedure, and it will also add in some canonical way. It will increase number of vertices by one, essentially by taking kind of a singular simplices with extra more vertex. By this extra vertex will be actually inside the original simplex, and there will also be a map rho from which we need should be from Cn of x to U of x, and they will satisfy the identity that we want for chain homotopy. Or I minus identity on of x. And it also will satisfy that the composition of just I with rho, the composition is the other way around, is just identity u of x. And then it will follow from this letter, the second map, it will just immediately follow that rho star times I star is identity on HNU of x. And here we also know that if if the difference between maps is of this form for some d, then it also follows that the push forwards on the homology groups are the same. And then from this, from this it follows that I star is an isomorphism. Again, if at the end of the next lecture I have more time, I will tell you explicitly more explicitly how to construct this rho. But this involves quite many technical details to do this properly. But again, the moral of the story is the operations involved to constructing this here is using this kind of barycentric subdivision and also kind of adding some vertices which are already like inside your singular simplex. So nothing too fancy. Okay, now suppose we have this. Suppose we have this technical lemma. How can we use it to prove the excision theorem? Proof of essentially a kind of almost all non-trivial proof is contained in the lemma, but okay, what is given we prove the lemma, what is the proof of the excision theorem? And as I said, it's kind of more natural to prove for version 2. So in the setup of the version 2, we have x containing A and B, and so that is covered by their interiors. And indeed, we just take our collection U to be collection of just two subspaces, A and B. And this lemma we had, so lemma tells us that there exists a chain homotopy D between identity This is between identity on Cn of X and the composition of inclusion rho. Lemma. And we also have just composition of and well, as I kind of described, so these so all these maps are obtained by some sort of constructed by some subdivision or restrictions. You don't, for any of these maps, you don't go outside of your like if you consider this map acting on some particular singular simplex, you don't go outside of the this singular simplex. You may divide it or restrict to some subsimplices and so on, but you don't go outside. And this means that all maps here, again, as usual, these all maps, so if you consider, they take if you consider singular simplex with image in some subspace A, it will be necessarily necessarily taken to some combination of singular simplexes also in the image contained in this A. So they take the subgroup Cn of A into Cn of A by construction, which again, I didn't spell you out how this construction is, but I roughly described this. And as they define induced maps on corresponding quotients as usual. Because again, this denominator is a quotient is mapped to a subspace inside, so it's a subgroup inside. Okay, and therefore, okay, let's consider, in particular, we can consider our, well, this is our CNU of X, the space of singular chains with the image either in A or in B. And we can quotient it with respect to singular chains with image in A. And so here in the numerator, we consider just singular chains in X. Denominator again Cn of A. So the original maps rho and I, they were acting like this between the corresponding numerators. So I was inclusion and rho was the map back. And since they preserve this subgroup Cn of A, we can they induce maps on the corresponding quotients. So we can divide by this Cn of A. But now we can notice that on the left, so again, the right, we have, okay, by definition, what we have Cn x comma A. But let's see what we have on the left. So on the left, this is, so in the numerator, we have singular chains in X with image either in A or in B. So it's generated by it's generated by singular simplices with image either in A or in B. And here we have a group generated by singular simplices in the image in A. So the quotient this quotient is the same as a quotient of so if you have something here which has image in A, we can forget about it because we have the quotient with respect to the scene in A. So we only can consider elements here which has the singular simplices which have image in B. And then it's enough to divide by the singular simplices with image in the intersection of A and B. The chains in B model chains in A. But of course, now we consider, we are only interested in the intersection of A in B. Well, okay, so, and this is, by definition, is the Cn for the pair B, comma, intersection of A and B. And again, so we had this I and rho, they were homotopy inverse. Inverse to each other. Meaning the difference satisfies is of the form like this. So the difference between identity. I mean, they exist. What means they exist chain homotopy between the compositions and identity maps. And this the same property will be preserved after taking this quotient, so they still will be homotopy inverse to each other, and this will follow that these corresponding induced maps on these quotients also isomorphisms on the corresponding homology groups for these quotients are also isomorphisms. So, and this is gives us statement of the excision theorem that the corresponding have induced, namely we have induced maps from Hn, so we have from Hn B, comma A intersection B, we have a I star to Hn X, comma A, and back we have rho star, and we have the property that this is identity. Also identity. This means they provide an isomorphism, and this is how you how one shows the statement of the excision theorem. Again, this was just an idea of the proof, and just to give you just intuition how this goes through. Are there any questions? The next lecture, we are, well, assuming that we have this statement of the Excision Theorem, we will show that this that under certain conditions have essentially isomorphism between the relative homology group for a pair and unrelated homology group for the quotient. Well, this is one has to clarify some things. So let me put it in quotation marks, which we will do next time. And we will show, and I will give examples how one can use this statement combined with a statement about long exact sequence property for these relative homology groups, how one can use this to make some statements for some particular examples of topological spaces. So far, yeah, this was quite abstract, but now we developed enough techniques to consider some particular examples. And again, if I happen to have extra time, I will tell you more details about this construction. I mean, the part which I skip, which is actually requires quite a lot of work, is construction of these maps. X. Well, essentially, you construct this map, and then rho you construct using this D. Okay, any questions? Okay, if no questions, that's it for today.
Professor, sorry.